I've been feeling it since 1966. Never had your fill, feel it still. Ooh, I'm a rebel just for kicks. Let me kick it like it's 1986. Might be over now, feel it still. We could find a war for peace. Giving to that easy living, goodbye to my hopes and dreams. Stop flipping for my enemies. We could wait until the walls come down. Someone give a little to the kids in the middle. Oh, telephone, won't bother me. Ooh, I'm a rebel just for kicks. Yeah, your lovers and abyss for my heart to eclipse now. Might be over now, but I feel it still. Ooh, I'm a rebel just for kicks now. I've been feeling it since 1966 now. Might be over now, but I feel it still. Ooh, I'm a rebel just for kicks now. Let me kick it like it's 1986 now. Might be over now, but I feel it still. Never had your fill, feel it still.
All right, let's go ahead and take a look at this first lecture survey question of the day. And the first one that's going to count really towards score in this course. Again, participation only. Let me switch my screen share. So question was, which of the following is consistent with our description of a technology? And last class, we certainly said it is an abstract relationship between inputs and outputs. So if you got that, definitely on the right track here. As we will see today, technology also defines the most you can get out of a particular set of inputs, as well as defining a minimum amount of input required to achieve a particular level of output. So if you said all the other choices are correct here, then you're a little ahead of the curve, and nicely done. If you didn't get it right, no worries, because these are graded on a participation basis only. You'll get full credit if you submit them. So again, if you're watching from home, make sure you submit these before Sunday at midnight. Also, after class, the first 5 questions for the LRPs will go up. They're coded the same way as the LSQs are. Again, those should be submitted prior to Sunday at midnight. I've also posted a bunch of worked problems in the problem sets and solutions module, problem sets from the regular quarter, old practice exams from the regular quarter. So lots of questions there to work from. I think for you now, problem set 1 will be relevant, as well as practice midterm exams 1A and 1B for the stuff we're going to cover in the coming 2 days, 2 to 3 days, maybe coming 2 weeks. So with that being said, I want to pick up about where we had left off last class in describing a technology. So let me switch my screen share back here. So what was a technology? Well, we said it's this abstract relationship that describes what goes into a productive process and what you are getting out of that productive process. Oh yeah, one real quick point here. Oh, my video just went out for some reason. Just a heads up, my computer's been acting a little funny today. If we crash out for some reason, I'm going to just switch to another laptop and we'll pick the meeting back up within 5 to 10 minutes. So just stay tuned. Don't leave if something happens. But just some good news for folks on the wait list. Thank you for reminding me. I did put in a request. I know I said I wouldn't, but I caved. I did put in a request to expand 20 additional seats in both sections. So if you're under number 20 on the waiting list in both sections, you should be admitted within a few days. I hope that helps the folks in that situation. If you're past 20, you know, you really got to just kind of tough it out, as we had mentioned before, but hopefully that makes life a little easier for you. I don't know why my camera stopped working. Anyway, we'll deal with it without the camera for now. So I think last class, we had jumped in and we were thinking about a very specific type of technology, and that was a coal-fired power plant, which was taking a very big set of inputs, things like capital, labor, different types of fuels, natural gas, oil, coal, and they spit out energy, right, in the form of electricity production, but they also generated some byproducts, right, pollutants that were maybe unintended outputs of that productive process. And what I want to start doing today is looking at different ways of actually thinking about orienting ourselves and describing a technology, which is really a very high dimensional and abstract thing that we're going to be looking at. This picture that we have on the right side of the screen, a few things you should take note of. First is the title is always important. We have energy generation on the vertical axis, gigawatt hours produced. On the horizontal axis, we have the heat content consumed. So this looks like energy going in is on the x-axis, energy coming out is on the y-axis, and all these different data points up here are different power plants in the United States measured at a given point in time. And you'll notice there's a little legend here that says some of these plants are regulated plants. Some of these plants are unregulated plants. The regulation that's being relevant here has to do with the Clean Air Act. However, if you look at this picture, I think there's a couple important things we can note here. First off, I want you to recognize that we're looking at an input-output orientation, right? An input-output space, meaning we're measuring an input on one axis, what's going in, that's the heat content, the energy we're consuming, and this is the amount of output we're getting out of it. Okay, now, if you look carefully at the slope of these lines, it's hard to see here, but there's actually two dotted lines. They're kind of right on top of each other. There's a red and a black regression line. Can anybody see approximately what the slope of that line would be in that diagram there? So it looks like here the rise is like 10, right? The run is maybe about 30. Is that correct? Rise is 10. Run is about 30. So yeah, the slope's about like a third, maybe somewhere in between. Maybe like a third or like a quarter or a fifth, somewhere in between there. Say it's a little bit higher than a fifth probably. But I want you to think about what that tells us about the energy going in versus the energy coming out. Are these power plants, do they seem efficient? Like you put in 30 gigawatt hours of heat content in, and how much do you get out? You only get what? You're only getting like a third of it. That's right. So from this perspective here, this input-output perspective, what we're looking at here is a slice of this technology. We're looking at it from a particular perspective. And on the horizontal axis, we have the heat content from using fuel. This is one way you can think of measuring the input. On the vertical axis, we have the actual amount of energy we generated. So it kind of looks like here from this picture that from the energy that goes in, they're wasting about 2/3 of it. Only about a third of it actually goes to producing electricity, which means the other 2/3 doesn't just disappear, right? Physics tells us, right? The law of conservation of mass energy tells us that that energy is going somewhere, and probably it's getting put into what? Yeah, it's getting put into pollutants, right? That are going into the atmosphere, excess heat, particulate matter generation, etc. Okay, now, this is one perspective we can look at things on. Here is a slightly different slice in terms of perspective. Now, I'm going to argue this is still an input-output orientation, but you'll notice now on the horizontal axis, the type of input has changed, right? What are we measuring there? Like in terms of factors of production. Yeah, it's really a labor input. I like what you all are saying there. Absolutely. We're looking at a labor input now. So it's like we have labor on the x-axis, right? Still though, energy generation on the y-axis. And again, hopefully we're recognizing that as the more labor we use increases, it looks like those power plants are able to generate more energy. Okay, so again, this is a slightly different orientation, still output on the vertical axis, but we have a different input on the horizontal axis. We're looking at a different slice of this technological process here. Okay. We could think about other types of inputs as well. For example, in this diagram, I have capital on the horizontal axis, still energy produced on the vertical axis. And you'll notice it looks like firms that are using more capital are able to produce more energy, which I think also, again, makes sense here. But my point is, if you have several different inputs, there's many different input-output slices or orientations you could think about looking at this technology from. Okay. Here is yet another one. Okay. Horizontal axis, we have, again, the heat content going in, but now I have how much pollutant we are generating measured in short tons. So we have an input on the x-axis, we have some sort of bad output or unintended byproduct on the vertical axis. Okay, if we wanted a different bad output on the vertical axis, we could again think about slicing the technology differently. Okay, and if you're looking at these plants, by the way, and wondering, oh man, there looks like a pretty important pattern between the red ones and the black ones. What do you notice is true? For any given value of the heat content consumed, what is true about the regulated plants compared to the unregulated plants on average? We'll notice what's happening there. Yeah, it looks like the regulated plants are producing more of that emission, okay, than the unregulated ones on average, right, at any level of heat content consumed. That is the reason why they were chosen to be regulated, by the way. If you're like, oh, shouldn't they be better than the unregulated ones? The answer is, this is the data that was used to decide which plants should be regulated or not. Now, another input-output orientation here, a different slice, right, of the technology. Right? We're dealing with a hyperdimensional thing, but here's another slice where, again, we have, some input on the x-axis here, heat content consumed, and we have a different bad output on the y-axis there, right? So nitrogen oxides this time instead of sulfur dioxide, just a different pollutant. So we could orient, right, inputs relative to outputs on the x-y axes. It's possible even we could think about multiple inputs on both axes, right? Here's an input perspective where we have labor on the x-axis, we have capital on the y-axis. And again, this is just a different, perspective, a different way to slice the technology and to look at relationships in that technology. Okay, here the relationship involving capital and labor. And it looks like the firms that are using more capital tend to need more employees to manipulate that capital, which I think makes sense. The more machines you have, the more people you need to operate them. But it's also possible for us to have, for example, an output-output orientation. Okay. Here we have two outputs on each axis. We have a good output on the vertical axis, and we have a bad output on the horizontal axis. And you're probably noting that all of the unregulated plants, the ones that were performing well in terms of whatever criteria were used to choose who was regulated or not, all are able to produce more energy for a given level of pollutant being generated here. So here we're looking at one output energy on the vertical axis, sulfur dioxide to pollutant on the horizontal. But we could also think about putting on the horizontal a different pollutant if we wanted to as well, right? We could put NOx on the horizontal, right? Intended output energy on the vertical axis. So point being here, there are many ways you could orient a technology by taking a two-dimensional slice of it across just an XY plane. All right, here's an output-output orientation where we have both pollutants on the vertical and horizontal axes here. Okay, so we're going to very quickly start focusing on a very, very specific situation, a very particular type of core model for this course. easily generalizable. But you could think very rapidly about this coal-fired power plant situation as being described as a multiple input, multiple output scenario. We kind of jumped right away into this data example with really the most complex case. And what we want to do here now is introduce a little bit of notation to describe theoretically our model of a technological process. So here's how we're going to do this. I'm going to use the vector X here. This is a little X with an arrow over its head. What that is going to represent is it's going to represent a list of the quantities of all the different inputs that the firm is using. So there are capital I inputs. X1 is the quantity of input 1 that is being used. X2 is the quantity of input 2. Maybe X1 is labor. X2 is capital. X3 is energy, so on and so forth. And we're going to assume here that the firm is producing J different outputs. Okay, in a moment, we're going to just focus on the case where J equals 1 and I equals 2. Okay, but we could think just for now about our general case, right? Where we're maybe producing multiple outputs. I have energy, I got sulfur dioxide, I got nitrogen oxides, right? Multiple outputs, multiple inputs. And the way we're going to model that black box technological process is with a functional relationship between X, the vector of inputs, and Q, the vector of outputs that we're going to refer to here as a production function. And in this particular case, the production function is taking those inputs, X, and it's actually spitting out an entire vector of outputs. And we're going to argue in a moment that this equation actually is describing the maximum amount of Q that could be generated with the given X, and at the same time, the minimum amount of X that is required to produce a particular value of that vector Q arrow over its head. Now, we're going to shift our attention for the moment to the 2 input, 1 output case, and we're going to really stay in this framework for probably most of the course. Again, this is a fairly simple model, and it is easily generalizable. All the lessons, for the most part, that we can learn with this model where we only have 2 inputs, we're going to assume they are capital and labor. Those inputs are being applied to a technology which is generating a single output Q. And in this framework, our production function F is going to provide us with a scalar value. It's going to provide us not with a vector of different outputs that we can produce. It's just going to spit out a number, and that number is going to be the maximum amount of output that can be generated from a particular input vector. So here is how we're going to think about our model that is going to be applicable for most of the course here, where we have, a couple inputs, capital and labor going in, and then it's spitting output out. All right, now I want to start looking first at the input-output orientations for this particular 3-dimensional technology. I'm saying it's 3-dimensional because we would have a capital axis, a labor axis. You can think of those like an XY axis. And then we have an output axis that's kind of maybe coming out of the board at our faces, if you will. What I want us to do is, instead of looking at the whole 3-dimensional technology in 3D, which we could actually do, I'll show you a 3D picture a little bit later. What I want us to do is think about slicing it along the QL plane. So we could think about looking at the relationship between output and the quantity of labor. And for the moment, we're going to assume that we are holding capital fixed. Capital, we're going to assume, is a fixed input. And does anybody remember what time horizon assumption this is consistent with? In which time horizon do we assume that some things are fixed, like the quantity of capital? Anybody remember? Yeah, Daniel, I like what you're saying. That's right. should be in the short run. That's an assumption typically made about the short run. And we'll elaborate more on that moving forward. Yeah, that's right. Matthew, Dylan, William. Yep, very good, folks. And if we were to graph the quantity of labor on the x-axis against output on the y-axis, what should the slope of that relationship generally look like? What do you think? Upward sloping, flat relationship, downward sloping relationship? What do you think we expect to see there based off of your not only economic intuition, but maybe physical intuition also? Okay, good. A lot of folks are saying we expect to see some sort of upward sloping relationship. Okay, I think that's reasonable, right? That means the more labor you use, the more output you can produce. You want to remember what that property is called. You might have seen this in 100A with utility functions, where the more you consume of something, the better off it makes you. Okay, it's related to marginal utility. Okay, but it's really an assumption about how things work. Yeah, Abel, I like what you're saying there. Okay, Abel's saying non-satiation. I'm going to use a different phrase. I'm just going to say more is better. You might have heard it referred to in that way. More labor, right, is better than less labor, and that more labor should be able to generate more output. Very similar to assuming that more is better on the consumption side as well. Just a heads up, I am getting an internet connection is unstable message right now. So if we do get chopped off here, if we get disconnected, just sit tight. I'll be back on in a few minutes on my other computer, hopefully with a good internet connection. That being said, we have an upward sloping relationship we expect to see here, but a couple other folks mentioned that it's probably not going to be just a straight line upward sloping, right? Like your intuition probably suggests that as we use more and more labor, right, maybe a straight line is not an appropriate model of the technological. All right, we are back. Sorry about that. We are still recording now. We're in good shape here. Let me just go ahead and share my screen again. And we should be good to go. Hopefully that does not happen very frequently. If it does, I will make adjustments accordingly. Everybody back, just shoot me a real quick message in the chat telling me that you're still seeing me and you can still hear me. All right, all good, wonderful. Hopefully my video is back now too. Excellent, good. You can see me as well here. So we were looking at this, and I think a couple folks said immediately, hey, we expect to see some sort of like diminishing returns effect going on with respect to this technological process. So that means maybe this is a more reasonable perspective to have. Would you all agree? Yeah, it looks like a little bit more reasonable here. Hey, as we're going to see in a moment, technologies can be very crazy. Okay, maybe they go like this, maybe they go like that. Okay, could have a variety of technologies. What we want to be able to do is keep an open mind and think about characterizing a wide array of technological processes. Okay, so we're going to start by kind of thinking about what might, an ideal technological relationship look like, right? Kind of a baseline relationship. And then we'll think about, how could we look at different models and what do those models imply about how inputs are being used and their relationships to output. But right now, if we implement this concave down assumption, this particular model of a technological process, then what we are doing is we're implementing an assumption about labor. Okay, what are we saying is happening to our labor as we use more of it? What happens? Is every unit of labor equally productive? Yeah, good. They're not equally productive, right? Every unit is becoming less and less marginally productive than the one prior, right? Capturing this idea of some sort of diminishing returns. Okay, and there's a reason why this happens, right? Capital, we said, was fixed. Don't forget about that, right? Capital was fixed. So for a fixed size factory, right? I have a factory, my machines are in there, I have a production line. Okay. That means if I add more and more workers in that factory, what starts to happen to those workers? Like the factory is this big, I keep jamming workers in there. Eventually, what's going to happen to those workers? Yeah, very good. Yeah, they're not getting as productive. That's right. Yeah, Uday, you might not see messages if they're not messaging you directly. Okay, but if folks have questions, they should be totally comfortable to reach out to you directly. That's totally fine. Yeah, no worries. Now, what I would like to do here is I want to introduce a concept known as a technology set. Okay. The technology set is defined by our production function. Okay? And the set itself is the feasible combinations of inputs and outputs. And when we say feasible, I want to be clear. We don't necessarily mean efficient. Okay, feasible means it's possible. And I'm going to use some formal mathematical definition of this set, and I'll explain exactly how to read this in a moment here. But the way to read this is that the set T, right, the set T is defined by the set of points Q, K, and L. Right, so it's defined by the set of points such that, okay, this vertical arrow here, it's a different color. Vertical arrow here means such that, set of points, such that, and then we have some condition that describes the set of points. And the condition is that the level of output, Q, has to be less than or equal to the maximum level of output as defined by our technological process. Okay, so what we're looking at here is set notation. We're saying T is the set of points, Q, K, and L. We can't see K in this picture because K is fixed. Don't forget we did that. Such that Q, the amount of output we produce, is feasible. It's less than or equal to the maximum level of output as defined by F. All right, so we want to remember here that F is defining the maximal level of output. Right, for a given set of inputs. Now, you'll notice there is a weak inequality here. Everyone see that? There is a less than or equal to sign. Okay. That less than or equal to sign tells us that we could be right on the green line, or we could be where? Yeah, we could be below it. So the technology set itself, T, is all of the area on the production function and below the production function. These are all feasible combinations of capital, labor, and output. Okay, specifically labor and output that we're looking at in this particular orientation. So again, F of K, right? That's measuring the maximum distance we could get, right, for a given level of L. Okay, but it's also possible that we produce less than that maximum amount, right? I don't have to be like right on the frontier here. I could be a little bit below it. Okay, this is possible. We could have points that are what we're going to define as productively inefficient that occur at the interior of that set T. All right. So if I was at some inefficient point, if I was in here, let's say, hey, there's two reasons why you could think this is inefficient. One is it's possible for us to move straight up and get more output for the given set of inputs we're using. But the other way you could think about inefficiency is if we're at that point, it's also possible for us to generate the same level of output by using way less labor. Okay, so the dark green boundary of this technology set, we're going to refer to that as the efficient boundary or the efficient frontier. Okay, and along the efficient frontier, what must be true? Well, that weak inequality has to hold as a strict inequality. So if we're talking about the points where Q equals F of KL, then we're not including the interior in this set anymore. That's in light green. We're just looking at the boundary of the set. In darker green, that's representing, again, one of two things. Representing the maximum amount of output that can be generated given a particular input vector, right? So if I wanted to use, this much labor, okay, then the production function tells me if I go up to it and over that that's the maximum amount of output that I can generate using that much labor. Okay. It also, though, at the same time represents the minimum input required to generate a given output level. So these two bullet points here are very related to that lecture survey question from today. Those were the other two choices aside from the choice whereby the technology is this abstract relationship between inputs and outputs. Now, the very first property folks had suggested when we started graphing the technology in this input-output orientation was that more labor should generally translate into more output, right? There was a monotonic relationship between labor and output. This is that more is better property. You may have heard this term used in your 100A class, depending on who taught it, of course. Where the more is better property, we would refer to that as you having monotonic preferences. If I give someone more of something, you can't make them worse off. If I add another worker to your assembly line, he can't make your production go down. If that worker was going to make your production go down, what could you do with that worker? Yeah, I just tell him, hey, just go stand in the corner. Right? Take him off the assembly line. You don't even need to fire him, actually. Just make him go stand in the corner. He was going to cause output to go down. You can waste that employee. Be wasteful. Don't employ him. Adding another employee should never make your output go down because you could always have the option of essentially benching that employee. Okay, so this restriction on the function, saying it's got to slope upwards, this is known as a monotonicity restriction. And we're going to assume that more of one input holding all other outputs fixed and all other inputs fixed, more of one input holding other inputs fixed will never cause your output to go down. And we're going to even take it to another extreme. We're going to assume it's going to cause your output to at least weakly go up. Okay, formally, we can impose this condition with a differential restriction on the production function. There's a condition on the derivative of f that we can use if we wanted to impose strict monotonicity. More labor generates more output. What does that condition have to be? What should be true about the derivative of f? Yeah, that's right. It should be positive. Right. So if the derivative of the production function with respect to the input is positive, we say that input has a strictly positive marginal product and it satisfies this monotonicity condition. It satisfies that more is better condition. Okay, note here, we've also defined the term marginal product of labor. Okay, it is the partial derivative of the production function with respect to labor. If we wanted to think about calculating the marginal product of capital, we would take essentially the same derivative, but with respect to capital, with respect to K instead of with respect to L. Now, the second restriction folks started suggesting was that, yeah, it should be upward sloping, but we should have this concave down shape. There should be some diminishing returns with respect to labor productivity. We should have diminishing marginal productivity, at least at some point, right? Maybe not first couple workers, but at least at some point, people are going to start getting crowded around too much capital, and they're going to become marginally unproductive. Okay, so if we want to think about placing this differential restriction on our production function in order to impose this diminishing marginal product condition, that means the rate at which output increases has to decline as more input increases, holding all other inputs fixed, meaning formally the differential restriction we're going to need on the production function to guarantee it satisfies this requirement and has this shape is going to involve restricting what? What are we going to restrict to make sure it has this shape? So first derivative's got to be positive. What else has to be true to make sure we have that concave down diminishing return shape? Yeah, Yaron, I like what you're saying there. Very good. A couple folks are saying the second derivative has to be negative. Okay, absolutely right. Okay, so if we want to satisfy this property of having diminishing marginal productivity, okay, then the second derivative should be negative, kind of like we have a frown face, right? Frown face, right? If you draw a sad face, right? You frown when you're feeling negative, okay? If we had a happy face type shape, right? Happy face, second derivative would be positive, right? You smile when you're feeling positive. Okay. So I think we're going to probably get into the lecture 3 slides. I tried to post them in advance. So if you're kind of wondering, are we out in the weeds here? You should be able to kind of follow along with that next slide deck. Now, terms of marginal product, right? This is a restriction on how the slope has to change. And we refer to this restriction as DMP. I'm going to abbreviate it for diminishing marginal product or diminishing marginal productivity. And this is the rate at which output increase declines as you increase your input, holding all other factors fixed using that ceteris paribus treatment. Ceteris paribus is the Greek term for holding all other things equal or all other factors fixed. And again, we formally impose that by having that negative second derivative, meaning the slope initially starts out pretty high, but as we increase L, the slope becomes smaller. It flattens out. So we can compute the marginal product. Okay, and we can think graphically about how we can measure the marginal product along the efficient frontier at a given point, right? If I gave you a very particular production vector, like I said, if we're going to produce, at this level of labor here, L hat, then we can go right up to the production function, compute that derivative, and we should be able to measure the slope of that tangent line, right? How productive are my units at the margin? Okay, the other thing we want to be able to compute is not just how productive is each worker at the margin, but I might be interested in how productive are my workers on average. Okay? And we can compute this measure of average productivity by taking the total output Q and just dividing it by the number of workers. Okay, that should make sense, right? If I produce 100 units and I have 5 units of labor, then on average, each unit of labor produced how much? We had produced 100 units. I had 5 workers do that. So on average, yeah, each worker produced 20 units, right? You took the Q, the 100, you divided it by the L, the 5. I think this definition might be even more straightforward than thinking about marginal productivity. Now, graphically, average product is a little stranger to see, but the way you can actually see it graphically, right, is if you draw a line from the origin to any point on the production function. Okay? Like if we consider the line, right, from the origin to this point, okay, and I think of measuring the slope of the blue line, right? I want to measure the slope of the ray from the origin extending to a point on the efficient frontier. So if I measure the slope, right, the rise is Q. The run is L. So when I do rise over run for the blue line, I am literally computing the average product of labor by doing that. Okay, and we'll go through a couple examples in just a moment. Now, I mentioned we would take a look at a 3-dimensional picture of our technology. Here is kind of a attempt at doing that, where you could think about on one axis, we have labor, on the other axis, we have capital, and on the y-axis here popping up, that's our output. And we can see this 3-dimensional surface here. I drew a very generic, I'm going to call this an S-shaped technology, because what we're going to do here is we're going to look at a very particular slice of this technology along this direction here. Kind of looks like an S. Imagine we slice it right down that plane, and we look at the technology in an input-output orientation. We would see something like this. Would you agree? Started here, take that slice, we wind up with this picture. And for a given level of capital. And what I would like us to think about here is for this type of technology, which I think is a very general type of situation, I want to think about the relationship between the marginal productivity and the average productivity. And we're going to make this argument for labor, but the same argument could be made for capital if you thought about slicing that technology in the capital direction. Okay, so it's a little bit more general than just a straight line or this, nice behaved concave function. I would argue this is maybe even a little bit more realistic in certain scenarios we could think about. But you'll notice this S-shaped technology, right? The marginal product does something a little odd. When we only hire like the very first worker and we put him in our factory, what's true about the marginal productivity of the very first worker? Really wanted to be extreme about it. Very first worker, marginal productivity is really low, right? You put him in there, he's got no other boss. The guy's just messing around, not very productive, can't even run the machines with one person, right? But then we add a second person and productivity at the margin starts to do what? Yeah, it starts to go up. Like 2 heads are better than 1. They can do even more than twice what that guy could do alone. Okay, but at some point, what starts to happen? At some point, we put enough workers on that assembly line and they start to get crowded, right? Workers are annoying. You got to listen to them. They complain. You're crowded. Everyone's trying to use the same printer at the same time or water cooler at the same time. Okay, so you may be well aware of that. Now, we should be able to see here that our marginal productivity, it is increasing at low levels of output, right? Low levels of output, it's increasing. And at some point, what happens to the slope? It's like increasing, 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 and then it decreases, which means at some point, the slope reaches a what? Going up, 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 and then it starts going down. Yeah, the slope reaches the steepest value. It reaches some maximum. Okay. Notice that occurs at like an intermediate range of labor utilization. That's as efficient as a worker could be is when you hire that guy right there. But at some point, we said diminishing returns is going to kick in. For a fixed level of capital, those workers start getting crowded around that capital. And then we expect that diminishing marginal productivity result to kick in. So you'll notice there's a range where marginal product is actually increasing. We don't exhibit that DMP property until we pass some threshold. And in that yellow region, we definitely exhibit diminishing marginal productivity there. Okay, so we can see here the marginal productivity is changing. We're going to think about graphing it in a moment. Started low, goes high, reaches a maximum, and then goes back down. So we'll be able to think about the graph of the marginal productivity of labor in just a moment. What I would like us to do is to think about comparing the marginal productivity to the average productivity at these different labor allocations that are drawn. Okay. In fact, I don't have one drawn here, but we could. And here's a red one there. Boom. All right. So average productivity. Okay, if I think about drawing a line from the origin to that first point, everybody agree that blue line got a pretty low slope there? Okay, but what starts to happen to the average productivity as I start hiring more productive workers? What do they do to the average? Yeah, they pull it up, right? So even though the marginal productivity started low, so did the average. But as we hired more productive people, they start to pull the average up. Okay, so we should be able to see that, right? We draw that point there. We can see the average begins to get pulled up. However, at some point, right, the marginally productive workers start to become less productive, which means when we start to hire them, they start to pull the average down. Okay, so it starts to decrease. But we should also note that there is an allocation where the average product also reaches a maximum value. Everyone see that right there? It reaches a maximum value right at that yellow point. And notice at that yellow point, the blue line also looks like it's tangent. Everybody agree? The blue line looks like it's tangent, meaning at that point, what has to be true about the average productivity and the marginal productivity? Yeah, they got to be the same. That's right. Very good. Got to be the same. And so we can think about, okay, well, if I wanted to maximize average productivity, that has to happen where the marginal product and the average product are the same. So what I would like to do here is use the graph on the right to plot our marginal productivity and average productivity values. And the way we're going to do this is we're going to think about a given level of labor. And I'm going to ask you in the right diagram, what is steeper? Is it the red line or is it the blue line at this particular level of labor? And it may be hard to tell. But at L1, you think the red line is steeper or the blue line is steeper? It looks like a lot of folks are agreeing that it's probably the red. I'm not sure what you're referring to, Scott. If you could elaborate. Was it the last slide? Yeah, let me jump back there real quick. Yeah, so it says APL reaches its maximum at this level of labor, but MPL reaches its maximum at L2. So I think that's correct, right? APL and MPL, they don't reach their maximum at the same value of labor. Yeah, no worries. Really good question. So back to it. We were looking at L1, and I think a lot of folks said it looks like the marginal product is higher than the average product at L1. So in the left picture, if I wanted to plot the values of MP and AP, everybody comfortable? MP in red is higher than AP initially. Okay, what about at L2? Which is higher, the average product, the slope of the blue line, or the marginal product, the slope of the red line? And still, it looks like the red is steeper. Okay. How does the slope of the red line at L2 compare to the slope of the red line at L1? Yeah, much steeper. Okay. So it looks like both the blue line and the red line are still steeper, okay, but still the red line is above the blue line in terms of the size of the slope. What happens at L3 though? What's true about the slopes of the blue line and the red line at L3? They're the same. Exactly. So let me just graph that as a purple dot. The red and the blue are right on top of each other. And then at L4, which one is steeper, the red or the blue? Now the blue is steeper, right? So I'm going to suggest what we've done in the left picture is we have graphed out a few points on the average product curve and on the marginal product curve. If we were to connect those dots, we can see the relationship between the average product function and the marginal product function, I think, fairly clearly. Okay. So there's an important feature of this diagram, a few important features, in fact. You'll notice in the region where the average is increasing, okay, in which region is the average increasing? From 0 to what? Yeah, from 0 to L3. Very good, Bryce. So everybody agree from 0 to L3, the average is going up. Why is the average going up? Well, let's think. Where is the marginal relative to the average in that region? Yeah, it's above it. So like if Jeff Bezos came into the Zoom meeting, right? What would his marginal contribution to the average wealth? What effect would he have on the average wealth of everybody in the Zoom meeting? Bezos walks in, pulls the average up, agreed? His marginal value is above average. So we should be able to see here why in this green region this makes sense. Because the marginal is above the average in that green region, the average is getting pulled up. Okay. However, past L3, the average gets pulled down. Why does that happen past L3? Yeah, it's because now the marginal's below the average. It's like somebody who has no income or wealth at all comes into the meeting. they pull the average down. Their marginal contribution is lower. So I'm going to suggest this relationship has to be true in general. I'm going to suggest. Okay, we started thinking about this for this S-shaped technology, but I'm going to prove this in a very general sense right now. Okay? And we're going to do this by leveraging the quotient rule from calculus. Hopefully you remember that one. If not, we'll do a real quick review of it. But I'm going to tell you what we're going to do here. I'm going to calculate an expression for the slope of the average product curve. Okay, that's what I want to do. I'm going to find an expression for the slope of the average product curve. And the slope of the average product curve, we would compute by taking the derivative of f divided by L with respect to L. Is that right? Here is our definition of average product. That is just Q divided by L. And I want to know the slope of that thing. So we're going to take the derivative. Now, if we're using the quotient rule, can anybody remember what goes in the bottom when you take the derivative using the quotient rule? Has to do with what was in the bottom of the original expression. Yeah, we're going to get the denominator squared. So we're going to have an L squared in the bottom. Okay, but in the top, we're going to first take the derivative of f times L, then minus the derivative of L times f. Here is our basic quotient. Any questions about that? Basic definition of the quotient. Okay. And the reason why I'm doing this again is I'm going to suggest that this is a generic relationship. Okay, this applies in general, not just to an S-shaped technology, but in general. Okay, now the next thing I'm going to do is I'm going to take one of the L's in the bottom. Everyone see we have two L's in the bottom. It's an L times an L, right? L squared. We got two L's down there. I'm going to pull one of those out and bring it up top. If I bring it up top, I have to flip it. Any problems with that? That L squared now becomes this 1 over L and this L. Any questions about that? Okay, again, the reason we're doing this is to show that in general, the average product and marginal products are related in this way that we've suggested visually. Okay, the next thing I'm going to do is I'm going to take that 1 over L and I'm going to distribute it in to each of these terms. Okay, you should see that this 1 over L and that L will cancel. But when we distribute it into the second term, we're going to get what? How are we going to interpret that when we distribute the 1 over L into that second term? We're going to take this, distribute it into that. How do we interpret that? It's going to be what? Yeah, it is the average product. Very good. Okay, so you should note we have two familiar things pop out in this step. Right, in the yellow, we got the marginal product. In the orange, we have the average product. Okay, and have I assumed anything about F at this point? Like in this proof, was there any assumption I made about F? Not really. Very general function F. This is truthful. Okay, now I'm going to suggest we're pretty much done with the proof. And here's what we've shown. We've shown that the slope of the average product, right, the slope of the blue curve, we can calculate by doing this thing. Okay. And we should be able to consider here three situations. We first had the situation where the average was getting pulled up, meaning the slope of APL had what sign? Average is getting pulled up. Slope of APL has what sign? Yeah, it's going to be positive. Very good. Okay, now, how can the slope of APL be positive? What has to be true about the marginal product compared to the average product to make that slope positive? It has to be the case that MPL is above APL. That is what is pulling up the average. Okay, the other case we saw we could be in is we could be to the right where the average product is decreasing. And that happens, right, when the derivative, the slope of the APL curve is negative. So the slope of the APL curve will only be negative when the marginal product is lower than the average product. That's going to cause the average productivity to decrease. Okay, now there's one more case. And the last case is, well, what happens if the two are equal to each other? Well, if they're equal, then we're at that special point right here where the average product reaches its what? Yeah, it reaches a max, right? The slope of the AP curve is 0 at that point. It's totally flat. And that happens when the marginal is equal to the average. This is a generic result that must hold in general. We didn't assume anything about F. And now, thus far, our focus has been on this input-output orientation. And we had output on the y-axis, we had input on the x-axis. What I want to do is change gears a little bit, and I want to think about looking at a different perspective of this three-dimensional technology. Okay, rather than slicing it across the input-output orientation, let's think about slicing it across the input-input orientation. So we're back in input space. We can also conceptualize technology sets within this particular orientation. Remember, the technology set was the set of points, right? Was the set of points such that production was feasible, right? This condition was satisfied. So it describes a set of feasible production vectors. Now, just like your 100A class, where you looked at input space with commodity bundles, right? They were inputs in the consumer's preference, and the preference then would spit out some utility values, right? Using a utility function, much like the way our technology spits out output using a production function. And we can now think about an input space looking at all of the different combinations of capital and labor that are capable of producing a particular level of output. Just like in 100A, you could look at an ISO utility curve or an indifference curve, if you will, right? That measured the set of bundles that made a consumer equally happy. So if we were to slice that three-dimensional curve horizontally at different levels of output, what we would see is essentially a map of these production indifference curves that we refer to as ISO quants. ISO means same, quant means quantity, right? Along this indifference curve here, if you will, these different combinations of K and L and the blue dots are all capable of producing the same level of output Q bar. Okay. And I'm going to suggest not only that, but the isoquant consists of the efficient combinations that can produce Q bar. I'm going to suggest this is in some regard an efficient frontier but in the input orientation, right? Like it's possible for us to produce Q bar with this much capital and labor. Everybody hopefully agrees. We can produce Q bar with that blue dot there. Okay, but I can also produce Q bar with this blue dot here. How do I know that's possible? We compare the first allocation to the second. What's true about that second blue dot that I drew? It's got more of what? It's got more of everything, right? Got more labor, got more capital. So if there's more labor and more capital, it can not only produce Q bar, it can probably produce even more. That's right. But my point is, if my goal is to produce Q bar, then at that higher point here with that purple arrows pointing towards, that's too much capital and labor for me. I could do better, reduce my costs of capital and labor, and still generate the same amount of output. Okay. So again, we're looking at a slice of the technology here. If we thought about looking at multiple slices on the same diagram, we could consider an entire isoquant map that shows us the various level curves corresponding to different production values. Okay. Now, just like you had properties that indifference curves generally should satisfy if they were considered to be well-behaved preferences, we also have some properties that should be satisfied for what I'm going to refer to as well-behaved or well-defined technologies. Okay, the first should be familiar, and that is your isoquant map should never involve two indifference curves that are crossing. Okay, they should never cross. If they cross, you can find a logical contradiction where you violate the monotonicity assumption. They should also slope downwards. If they're sloping upwards, that means one of your goods is actually a bad. You have some sort of bad input that hurts your production. They should also be bowed inward to the origin. And this is similar to that diminishing marginal rate of substitution assumption. We're going to call this the diminishing marginal rate of technical substitution in a moment, probably next class, since we're a little short on time here. And again, higher isoquants, right? Higher indifference curves up and to the right correspond to more in terms of more capital and more labor on average. And we know more is better in terms of monotonicity. Higher isoquants should yield higher output levels than lower isoquants. Okay, now we can also think about technology sets in this input space. Recall the technology set was given by this expression here. And in the right-hand diagram now, we can think about the feasible production vectors. We argued you could be right on the boundary if you're efficient at Q bar, right? Like we would be at allocation A. Right? Formally, we say A is part of the technology, right? It's a vector in the technology. It's an element of the technology, if you will. And A requires the minimal amount of capital and labor in a way that it's falling on the efficient boundary of the technology. But now we're efficient with respect to this input-input orientation. So formally, we could say, hey, A is actually on the boundary of T. It's not only in T itself, but it's on the boundary of T. Okay? We could consider inefficient allocations like allocation B in this picture here. Okay, allocation B is also in the technology set, but we should notice that B falls in the interior of the technology set, indicating that it is not an efficient allocation. Like we can connect B and A on a straight line through the origin and see that if we cut back on capital and labor both by the same factor, we can scale B down to A and we can still produce Q bar. So unfortunately, B is inefficient. We say that B belongs to the interior of that set T, and the interior of T is the inefficient portion of T. B is not a part of the boundary, and the boundary being the efficient portion of T. So yeah, that's right. B is possible. It's just inefficient. I'm using too much K and L. And if I'm using too much K and L, right, they're not free. I have to pay my workers a wage. I got to pay my capital owners profits. So if I'm using too much K and L, that means my costs of producing Q bar will be higher than what they would be if I was to reduce them at point A. Hopefully that answers your question there, Emily. Really good question. We should also note that if you take the intersection of the the union of the interior and the boundary, okay, that is the full technology. That's the same thing as taking the union of the efficient part of the technology and the inefficient part of the technology. So before we wrap up today, I want to think about now trade-offs along the efficient frontier that are implied between capital and labor if we wanted to reshuffle our allocation of inputs, but produce the same quantity Q bar. Okay. If we cut back on labor and I want to produce Q bar, that's going to require me to substitute some capital, assuming, of course, that monotonicity holds. Okay, and this trade-off, right? We could think about measuring the slope implied by that trade-off there. And we have a very particular name for the slope of the isoquant. We refer to this as the marginal rate of technical substitution, or the MRTS, the marginal rate of technical substitution. And I think I will wrap things up here for this evening. I think this is the appropriate place for us to leave things off. Got about 5 minutes left, so let's just do a little bit of rapid fire Q&A. Any questions folks have, drop them in the chat. Hang out for a couple minutes, but then I got to get to my next section here. If there are no questions, then I will hand things over to Uday, who has the co-hosting conch shell here. But any questions, feel free to drop them in the chat. Happy to take those. If not, have a wonderful day. Have a wonderful Wednesday. Get over that hump, and I will see you all on Thursday, same time, same place. Okay. A couple questions. First question, for the quiz on Sunday, can we use our internet? There is no quiz on Sunday. Please read the syllabus carefully. Next question. The equations aren't showing up on the slides. You got to open them in PowerPoint, then they should be fine. Print them to PDF, open them in PowerPoint. If you're looking at them through the Canvas viewer, things might be jumbled. If you're on a Mac, things might be jumbled. If you look at them in PowerPoint, you should be good to go. For output space, can technology set on the boundary? I'm not sure what you're asking me there, Michelle. If you can clarify, happy to circle back. Can I go back to the slide on well-behaved technologies? I sure can. There we are. Yeah, if you print the slides out in OneNote, you should also be able to see all the functions as well. So if you're having that issue, there's a lot of different ways around it. Should not be a problem.